Hello, year 11. So I hope you've had a lovely half term. And today we're going to be looking at reflection and refraction. Now, these are the higher concepts. However, I think it's really important that we all have a go at these because these themes appear in both the foundation and the higher paper. Please don't become frustrated if you can't do it. I have just set a spelling test at the end, so there is no panic about there being another activity to do. All I want you to do is have a go at the spelling test, and hopefully that should relieve some of the pressure. Okay, so these are our learning outcomes for today, and we will move on. So again, you can support this using the Knole textbook. I've also added a bite-sized video for you to have a look at. And we are looking at pages 140 to 141 in the Knole online textbook. Again, email me if you don't know how to get to that, but it's there. You can use it. If you get bored of listening to me, you can just work through that instead. So, quick quiz. Number 1, what is the difference between a longitudinal and a transverse wave? Number 2, draw and label the transverse wave. Number 3, what is the formula for wave speed? And number 4, sound waves in air travel at the speed of 440 meters a second. Calculate how far they travel in air in 5 seconds. And calculate their wavelength if their frequency is 3 kilohertz. Okay, pause the slide. Have a go at those questions. I'm going to put the answers up in a second. So, longitudinal waves oscillate parallel to the direction of energy transfer of the wave. Transverse waves oscillate perpendicular to the direction of energy transfer of waves. Here's my beautiful wavelength. Make sure you've labelled it properly for me. Formula that we need to know, wave speed equals frequency times wavelength. And part A, the answer is 1700 metres. Part B is the wavelength is 0.11 metres. So wave fronts. There's a little bit of drawing to do here, so it'd be really useful if you haven't got one to hand. It's just maybe grab a ruler or use the side of your phone, whatever else is to hand. Okay. So what we've got here is waves can be drawn using lines called wave fronts, and each wave front is the peak of a transverse wave or the compression of a longitudinal wave. So here's my wave, and here's the direction of energy transfer, giving me my wave direction. And this is my wave direction. And this is what the wave fronts would look like. So you can see that the peak here is in line with the peaks at the front. Okay, so the difference between these two wave fronts is equal to 1 wavelength. It still gives me my wave direction, but we talk about it being a ray direction. And we talk about these being circular wave fronts. Now, when we've got a wave direction and it's not circular, we talk about them being plane. And that's plane as in aeroplane, not plane as in plain paper. So that's plane. Again, the difference between the wave front lines is equal to 1 wavelength, and it does give me my ray direction, my movement. All right. And we can investigate these using a ripple tank. Now, you may have seen these around the science department. Personally, they're the bane of my life because there was leak water everywhere, but we will be looking at these back when you're back in school. So reflection of waves can be investigated using a ripple tank. And the behaviour of the wave will change at the end of a medium or when it's moving from one medium to another. So when we're talking about medium, we're talking about either air to water, water to air. We can be looking at moving it through glass, all of those things. So behaviour itself changes on a 2-dimensional wave. So the water wave travelling through ocean water, and in a 3-dimensional wave, sound, light travelling through air. Study of waves has 2 dimensions and is usually done in a ripple tank. So it's difficult to investigate sound or light waves in a ripple tank because we can only really investigate 2-dimensional. So our ripple tank. Ripples are tiny waves sent across the surface of water. A bit like when you throw a stone into a pond, you see ripples on the surface. Obstacles are put in their path, so that blocks, bricks, whatever, and we see what effects are produced. You could be asked to describe these effects or potential effects in an exam. So let's have a look. So the ripple tank has a glass bottom, okay? And the light shining on the ripple tank will produce bright and dim spots on the paper screen. So this is my light shining from above, and this is when the light is shining through the water at its deepest, will give me darker shadows because the light has had to travel through a larger distance. So the crest of a wave, the top of a wave, the peak of a wave will absorb more light than the trough. Therefore, we get these bands of dark light. And it looks a little bit like this, okay? So we've got a lamp at the top, which gives us our light source. We've got this vibrating block, it has a little motor on it, and it produces ripples moving through the water. Underneath, we get shadows. Again, those dark shadows are my peaks of my waves, and the lighter bands of colour are my troughs. So, straight waves, plane wavefronts are produced using a straight object like a pencil or a ruler attached to the vibrator. Okay, and circular waves, circular wavefronts, are produced by using pointed objects such as the tip of a pencil attached or the tip of a needle attached to the vibrator. Now, here we are. We've got a really good video for you to watch. What I want you to be able to do is go through this and see how it works. You can see in the video that it shows you the nice light and dark bands. It can also explain how a plane and a circular wave are generated. So, the reflection of waves. And this is where, hopefully, this should recall some of the stuff that we've done in year 8. So we put a vertical surface in the path of the waves. So what we're putting into there is something with a nice straight edge, and the waves are reflected from that surface at the same angle they strike at it. Now, to see this happening, it's really good to be able to put that vertical surface, that nice straight surface, at a bit of a 45-degree angle, because then you can see the waves bouncing off. We know that a wave is reflected if there is no change in frequency and there is no change in wavelength and there's no change in speed. The only thing that there is a change in direction. Okay, so they're my key features of a reflected wave. These are often one of those tick box questions on exams, like which ones are true, which ones are not true. So record those for yourself if you haven't already done so. So here's an example of a reflected wave. So my instant waves are moving forward. I've got my reflected waves moving backwards. I've got my barrier. Now here we can see the waves travelling to the barrier. Okay, my vertical surface. And when they hit the barrier, they then are reflected. But they are reflected perpendicular to the barrier that they've struck. Okay. And we call that the reflected ray. And we call the wave moving forward is the incident ray. On the top one, it would be really difficult to see the reflected and the incident, difference between the incident and the reflected rays, because they're both at right angles to each other. And that's why when we look at the barrier and the bottom one, it's also useful to have it at an angle so you can see them. However, there is a simple equation, and again I'm hoping that the angle of incident is equal to the angle of reflection. So if they give you the incident ray or the reflected ray, that we know that the angle on the other side, if we draw that right angle tangent through to the box, is there. So check your understanding. Explain the type of wavefront shown for 1 and 2. So 1 is a plain wavefronts, okay, and type 2 is a circular wavefront, okay. Check your understanding on this. So we do call that line between the barrier at a right angle the normal or the norm, okay, and it is always 90 degrees, just so you're aware. So question 3, name the effect shown, and it is reflection. 1 and 2, name the 1 and 2 with appropriate terms. Incident ray, reflected ray, and if it strikes it at 30 degrees, then it must be reflected at 30 degrees. So, rare refraction of waves, and this is where a flat piece of plastic makes the water more shallow at a certain point. A bit like if you've ever been to one of those swimming pools that have one of those movable floors, you can have like different depths. It's the same thing. So, or you have an obstacle like a cliff shelf in the water at the beach. So when the waves move slowly, they change direction, and this effect is called rare refraction. Refraction, sorry. Okay, and there is no change to the frequency of the wave, but the decrease in speed means that the wavefronts close up on each other. So according to the wave equation, V equals F times lambda, as frequency remains constant, the decrease in speed causes a decrease in wavelength. So the direction of the wave travel changes unless they're travelling at right angles to the boundary. Okay? So let's look at that as a diagram. So here I have my ripple tank, and what I would see if I put a glass block just to make it shallower here is that the wavelength is the same until it hits the glass block, and then we can see that the wavelength becomes smaller, okay, and as they ripple in the shallower water, we can see that the waves change direction. However, once they exit, they continue. So, check your understanding. Name the effect shown. That's rare refraction. What type of medium could be in the regions 1, 2, and 3? So, deep or less dense. So if we used a thicker liquid, that would work as well. Or we could use a shallower for region 2. So, in which region will the frequency be highest? And the frequency is constant in all 3 regions. The wavelength and the speed change, but the frequency doesn't. How do you find certain region? How can you find a certain region is shallow? You can use it by the bending of the ray towards the normal. And the wavefronts of less speed show a certain region is shallow. Compare the speed to the waves in region 1 and 2 to 1 and 3. Explain your answer. This is really a grade 9 explanation. So don't panic if you're thinking, I haven't got a clue. Look at the explanation. When you see those really difficult questions, just give it a go. Don't panic. Just write down what you do know. Because actually, the odds are on those higher questions, you will get some marks. You might not get all 4 or all 6 marks, but you will get some. And if you leave it blank, you will always get nothing. So it says here that the waves in region 2 travel with less speed compared to the regions 1 and 3. The wavelengths are closer in region 2 and in region 1 and 3. However, the short wavelengths with no change in frequency the speed is reduced at region 2. So this is a practical application. If we've got an island, okay, in the middle of a stream, and the waves hit that island, what happens? Refraction occurs. So there's no change in frequency, but the wavelength reduces, hence the speed of the wavelength decreases. And reflection of waves does occur, and there is no change in speed, frequency, or wavelength. Now, that seems to have been a lot to go through, and I'm sure that you're sitting there thinking, whoa, my head hurts. So what I've done here is summarise this with 4 key points that you can write down to summarise today's lesson. I've also added a bite-sized video, and I would now like you to have a go at the spelling test. Okay, take care, and I'll see you again tomorrow. Bye.